Alright, in the previous lecture, we talked about the basic concepts and elements of data models. We learned that in order to have computers to help us to solve geographic problems, we need to communicate with computers. As you remember, data model is a translator between human perception and the computer. Basically, it translates our natural language into machine language so that computers can understand us. We discussed that data models can help us to stratify the real world into several layers or feature classes. And each layer is further abstracted as point, line, and polygon for object features, or a smooth surface for field features. All these features have their own geometry and attributes, which then can be coded by spatial coordinates and also tables, and computers can understand these. So with this background knowledge, I'm going to introduce you two widely used data models in GIS, including the vector data model and raster data model. And then we will compare them, their differences, their pros and cons, and whether they are convertible to each other or not. So let's start with vector data model. Vector data model uses sets of coordinates to describe geographic features, or more specifically, object geographic features. You can use one pair of coordinates to define a point, or then you can use a series of coordinates to construct line or polylines, and you can use a series of coordinates to construct a polygon. So that's basically vector data model. The key point in vector data model is using coordinates to define points, line, and polygons. So here is an example of how vector data model can represent reality. So this one is reality and this one is vector data model. So in reality, we have trees, we have a stream, we have lake. So you can see each tree here. Each tree can be abstracted or recorded as points, which is a one pair of coordinate. Okay, so this one is xy, x1, y1, x2, y2, and x3, y3. So we abstract the trees with one point or one pair of coordinates. This river or stream can be abstracted or recorded as polyline. Okay, so that's a series of coordinates. So x1, y1, x2, y2, x3, y3, and all the way up to xn, yn. And this lake can be abstracted as polygon, right? It's recorded as a number of paired series of coordinates. Let's say this one is x1, y1, x1, y1, x2, y2, x3, y3, and all the way up to xn, yn, and then x1, y1. So the coordinate of the beginning and end point is the same. So that's the definition of the, that's how polygons are recorded in vector data model. So again, we use coordinates to represent the real world. That's vector data model. And the shapefile format that you used in the lab is one of the most common type of vector data model. Shapefile is compatible with almost all GIS software such as ArcGIS, QGIS, MapInfo, GeoMedia, and so on. Also note that the same features may be represented differently depending on your interest and purpose. For example, here we have a couple of households or buildings. If you only need the location of buildings, you can just simply represent them as points. Or sometimes you may need to display the outline of the buildings, or you want to measure the perimeter or circumference of the buildings. In this case, you can represent them as polylines. In other case, you probably want to measure the area or coverage or the square feet of buildings. You can represent them as polygons. So the same feature can be represented differently based on the convenience, based on your needs. So this is how we record the spatial and attribute components of vector data model together in computer. So each feature on the map, so we have 1, 2, 3, 4 features on the map, will have a unique ID, okay? And each feature is linked to one row or one record in the attribute table. Okay, so for example, polygon 4 has a unique ID of 4, and then this ID refers to the row number 4 in the attribute table. And in such way we can use these attributes, so we can have all of these attributes, for example the type and also the area, as the attributes to describe this location. Okay, so for polygon number 4, which can be a county, it can be a country, it can be a lake, it can be building, or any polygon feature, we will have attributes such as type, area, it can be population, it can be number of people living in this polygon with the age of over 65. Any type of attributes is recorded as column, right? So this is how geometry or spatial and attributes are linked together in vector data model in computers. A special feature for the vector data model is topology. What is topology? Topology is the third type information and only is used in vector data model, in addition to geometry and attribute, in addition to spatial and attribute. Topological information are optional, and topological information basically record the spatial relationship between geographic features, such as connectivity, adjacency, and composition. For example, the state of Ohio is adjacent to Pennsylvania state. So adjacency of two polygon features, because they share borders, they share boundary, Ohio and Pennsylvania. I-71 interstate highway is connected to I-90 at Cleveland. Okay, this is connectivity between two line features. So again, it's between two features, two or more features, or the relationship between the features. Okay, it's not just one feature. And in this figure, we can say polygon A is composed of lines A1, A2, and A3. So composition is another type of topological relationship. So topology records relationship between geographic features, and it includes connectivity, adjacency, and composition between geographic features. A fancy characteristics about topology is its independency from geometry. From topological perspective, a donut and a coffee mug are similar. They are connected because it's like two features that are connected to each other. Okay, so we only care about the relationship between the features, and we don't look at the shape of the features. Okay, so this means that however the shape are different, the relationship is the same, so they are similar in terms of topological relationship. Okay, so let's look at these two graphs. Even though they have different shapes, right, the topological relationship remains the same. So from topological perspective, these two are similar. Why? Because, for example, polygon A here is adjacent to polygon B and also polygon C, right? Because they share borders. And also here, polygon A is adjacent to polygon B and also polygon C. Or we can say that polygon A is composed of A1, A2, and A3. And here also A1, A2, and A3. Or A1 and A2 are connected in point 1, right? A1 and A2 are connected in point 1. So from topological relationship, these two are similar to each other because we only look at the relationship between the features, not the shape of the features. Okay, so what is the application of topology? In some analysis in GIS, we need to set topology before doing the analysis. For example, in network analysis, to find the shortest path between 2 points, we have to make sure that the rows are connected to each other. So we have to set topology first. So I put some slides about topology and I suggest you to review them. For example, how GIS records topology as 3 different tables, and also what are the pros and also what are the cons of the topology, okay? But these slides are not in the exam. Now let's move on to the other data model, which is raster data model. What is raster data model? Raster data model, we use real world or feature class as a grid or matrix of cells, and each cell can be used to represent one point, and then you can further use multiple points to construct lines and areas. So each cell can have only a single value as the attribute of the cell, and different attributes show different geographic features, okay? So the positions of geographic features are defined by column and row numbers in the grid, and it starts from here. It starts from lower left corner. So the difference between raster data model and vector data model is that raster data model uses cells or pixels to represent point, to represent line, and to represent polygon. So that's the major difference between the vector data model and raster data model. In vector data model was based on the coordinate, but here is based on the cells or pixels. So this picture shows you a representation of reality using raster data model. In vector data model, which is this one, we abstracted them as layers of interest such as a river or a road or buildings. But in raster data model, we use cells to construct lines, right? To construct roads, to construct buildings. And then we can use different attributes for the cells. For example, the value for the building is 10, the value for river is 20, but the value for the roads is 30, okay? So we change the value, each pixel has a value, and based on the value we can define the features, okay? Let's load an image, which is an example of raster data model in ArcMap, okay? So I think I have an image here. Let me download. Okay, so I have downloaded an image in download folder, and I want to add it into ArcMap. Okay, so this is an image. So if I use this zoom in, and then if I zoom several times, what do I see is that so any image works, okay? So you can see that it's this image consists of several squares, right? So if you zoom in multiple times, you see some squares in the image. So these are the same. These are the cells or pixels, and the pixels only accept a single value. So if you use a identify button and then you click on that, so it gives you a single value, okay, for the R, G, and B. So which one was that? So for example, this one. So if I click on different points of this one, you can see that the RGB doesn't change because it accepts only a single value. But if I click on this one, just look at the value of RGB, it changes, right? But each pixel only accepts one value. So that's the raster data model, okay? And the entire image is a grid or matrix of cell. So the image we use every day are typical raster representation of real world, and each pixel of image is actually a cell. So that's why raster data model are widely used in GIS, because many GIS data are actually images, like satellite images. So for example, digital elevation model or DEM and temperature are widely used raster data. We can't use point, line, polygons to represent elevation, right? Or we can't use point, line, polygons to represent temperature. We use continuous surface because these are field feature, okay? So it's hard to identify their borders. So in a digital elevation model or DEM, each cell has a value corresponding to its elevation. So for example, in these areas we have these are highland areas, okay, or mountainous areas, and these areas are lowland areas. Or for temperature, as we move to northern latitude, we have lower temperature, right? So these are examples of the raster data model: temperature, humidity, precipitation maps, or elevation maps. So these are, or vegetation cover. So these are examples of the raster data models. So there is an important parameter for the raster data model, which is called spatial resolution, also known as cell size of the raster data. So the finer the cell size, the more precise representation of the real world. So here you can see a transition of the cell size from large cell size is 8 meters to small cell size, or 1 meter. So you can see more details can be represented in the small cell size. So this one is called a good resolution. And on the other hand, a smaller cell size means a larger file. Okay, for example, this one is like 100 megabyte, but this one is only 1 megabyte. Okay, so a finer resolution leads to a larger file, and also a slowness in display, okay, because computers need to load a larger file. For example, if you have DEM, or digital elevation model, for the entire United States with 30 meter spatial resolution, it may take a few minutes for loading. But if you use 1000 meter spatial resolution, it only takes few seconds for loading. So larger cell size like this, it means that it also called coarse spatial resolution, meaning that it has low resolution. So notice here we say spatial resolution is 8 meter. We don't say 8 by 8 because a resolution is cell size, right? We don't say 8 by 8 because we know that the cells are a square. So for the sake of simplicity, we only say that it's 8 meters as a spatial resolution. So now let's talk about the spatial coordinate of cells. So instead of directly recording XY coordinate, raster data model uses column and row numbers to represent the spatial location of geographic features. So how we can calculate the spatial coordinate for a given cell, for this cell, for example, first of all, even though a cell covers an area, right? So this one covers an area. We only consider its centroid, its middle point, to represent the location of the cell, okay? So when we talk about the cell location, it always means the location of the middle point in the cell. So the location of the middle point of the cell, or the location of the cell, can be calculated by having three conditions. First of all, we need to know cell size, or cell dimension, or spatial resolution, okay? And also we need to know the coordinates of lower left cell size, which is this one. So this one is the origin, okay? So we need to know the coordinates of the lower left cell size. And third condition is that we should know the cell row and column number for a given cell, for the cell that you want to calculate the coordinate for it, okay? So you have to count from here, okay? For example, for this one, the column number will be 1, 2, 3, 4, 5, 6, and row number is going to be 1, 2. So it is calculated from the lower left. Once you know the three conditions, you just plug them into this formula, and you can directly calculate the XY coordinates for any given cell in this raster. So let's see an example. Let's say you have a raster grid. The cell size is 30 meters. As I said, we simply say 30 meters rather than 30 by 30 because it has a square shape. And also we know the coordinates of lower left corner, which is 30, 75. And we want to know the spatial coordinates of a cell at row number 2 and column number 6. Counting from lower left corner. Okay, so first of all, we have to know where it is. Okay, so if this is your raster, the location, this cell is row number 2 and column number 6, which is going to be 1, 2, row number 2 and column 6, 1, 2, 3, 4, 5, 6. So it's going to be this location. Okay, so we just need to bring these three conditions to the formula. Okay, so x coordinate, so we have to we want to know the x coordinate for this location and y coordinate. Okay, so x for the lower left, which is 30, plus row plus column number, which was 6 minus 1, multiplied by the cell size, which is 30, right, according to the question. So it gives us x coordinate for this location is 180, and for y coordinates it's going to be y for this location, which is 75, plus row number minus 1, which is 2 minus 1, times the cell size, which is 30, which gives us 105. So we can have x coordinate and y coordinate for all of the cells in the raster. Another easy way to calculate the coordinate for each location is just you can easily count it, right? So this one, the x is 30, right? So 1, 2, 3, 4, 5. So 5 times 30, because between here from center to here, this center is 30, right? Because the cell size is 30. So 5 times 30 is 150, plus 30 gives us 180. Okay, or here the y is 75, we just need to go one cell size, which is 75 plus 30 is 105. Okay, so what do you think about this location? So it's gonna be one cell size to the x and one cell size to the y. It's gonna be 30 plus 30, 75 plus 30. That's the coordinates for this location. So you can easily calculate the coordinate for all of the cells in this raster. Let's look at the attributes of cell. So as we know, each cell can only have a single value as the attributes of the cell in the raster data model. So what if a cell covers multiple features? Okay, so for example, in this picture, let's look at cell B. Okay, this cell actually covers two types of geographic features. The dark area represents water bodies, and the bright area is the farmland. So both features are in this cell and in cell number B. So question is which value we should assign to this cell, because remember, a cell only accepts one value, water body or farmlands. In this case, we should apply a strategy, we call it winner take all strategy, which means that cells are usually assigned the value of the feature taking up the greatest part of the cell area, or simply which one has largest share. Okay, so which one has largest share? It is farmland or water bodies? Obviously water body has the largest share. Okay, so which means that we should assign cell B as water. Okay, and that's the winner take all strategy. Okay, for example, for A, if it's water and farmland, definitely has to be farmland, because farmland takes up the largest share, and so we have to apply the winner take all strategy for all of the cells in this raster. Okay, so in the vector data model, like a shapefile, for each feature we had one record or one row in the attribute table, right? But in the raster data model, each row in the attribute table does not describe a single cell on the map, okay, or image. But each row in the attribute table for the raster is a collection of cells, okay, which is the total number of the cells with the same value. Okay, for example, here all of the cells are 15, right? So, and there is gonna be just one record with the value of the 15, and also we have another field with area, which is the total area with the value of the 15. Okay, so it is not only one cell, but it's a collection of cells with the same value. That's one row in the attribute table. That's another difference between the raster and vector data model. So now we talked about two types of GIS data model, vector data model and raster data model. So let's compare vector and raster data model and see what are the pros and cons of them and how we can convert them to each other. First of all, both models, both raster and vector data models, can be used to represent points, line, and polygons, and also surfaces, right? Differences between raster and vector model is that in the vector data model uses pairs of coordinates to represent point, line, and polygon, but raster data model uses grids of cells to do the same thing. So that's the major difference between the vector and raster data model. And second difference is that the real world can be abstracted as a mixture of raster and vector layers. Okay, for example, for land use and elevation here. So we have land use and also we have elevation. You can use raster data model, right? So these are rasters. Okay, but for the street network, this one, for the parcel and administrative boundaries, they use a vector data models. Okay, so the real world can be abstracted. So if we combine them together, we can create the real world, right? So the real world can be abstracted as the combination of the vector and raster data model. But one thing that you should consider, you should keep in mind, is that if you want to overlay or combine these layers together, all these layers should share common coordinate system, which means that they should have the same origin and also the same unit. So you cannot overlay layers with miles as units and the other one as, I don't know, decimal degree as units. So in this case, we have to use reclassification, which we will talk about that in the future lectures. So now let's do the comparison between the raster and vector data model in terms of different characteristics. First, let's talk about representation. So raster data model is widely used to represent field feature. Remember, field feature were those that it was hard to identify their boundaries, like Wi-Fi, like temperature, terrain surface, humidity. So we cannot easily identify their geographic boundaries, right? In this case, we use raster data model. On the other hand, the vector data model is very good for representing objects feature, which was easy to identify their boundaries, right? Such as buildings, individuals, rivers, and other objects. So we use a vector data model for the object features, and raster is used for field features. Regarding the storage requirement, raster data model is usually very redundant and cost more data storage than the vector data model. Why? Think about Lake Erie. For vector data model, you only need to record the importance nodes along the boundary of the lake, right? And then you can complete the polygon. So it's going to be a one simple polygon. But for raster data model, you need many cells to fill this polygon, right? Just imagine if the spatial resolution was 10 meters, how many cells you need to cover the entire lake area. So that's why raster data model is more redundant, but vector data model is compact. And regarding topology, which is a spatial feature for only vector data model, it means that topology is the relationship between the geographic features, right, such as connectivity, adjacency, and composition. For raster data model, we cannot record the topological information, but in vector data model, we may have topological relationship. Remember, topology was an optional feature for vector data model that we will use it in the network analysis. For spatial accuracy, raster data model usually have lower spatial accuracy. Depending on the cell size, if we have 1 meter cell size, it is more accurate than 10 meter cell size. But generally, because every cell can only be assigned by one value, and we have to apply winner-take-all strategy for the raster data model, which means that we are losing information, we are losing spatial accuracy. and some details are missed, right? But vector data model, potentially it has excellent positional accuracy because you don't have to worry about the cells and losing much information by considering only the center of the cell, right? And in terms of compatibility of computer programming, raster data model is actually better than vector data model because it's very easy to code array structure, right? Raster data model is matrix, right? So, and most computer language are familiar. There are a lot of mathematical or computer algorithm to deal with matrix, right? So the vector data model is much more complicated. Think about vector data model, which has bunch of attribute tables and 3 topological tables and has a very complicated structure which cannot be easily handled by computers. How about the display and output? Raster data model is very good for field feature in terms of displaying an output, right? Like temperature or digital elevation model. But for discrete features, raster data model, it may show stair-like boundaries, right? So let's, for example, let's look at this one. Okay, so here, so you can see that when we use raster data model to show the this feature, it's like a stair-like, right? And because the boundaries is recorded as cells, and for vector data model, you can see that it has a very good, it's very excellent for displaying object features, okay, which has discrete boundaries. For analysis, so it depends on the type of analysis. Raster data is easy for overlaying analysis, especially when you want to combine data from multiple sources. Raster data is the priority because it's matrix algebra and you can easily add the two matrices together. But vector data model is very good at network analysis. In transportation, you want to find the shortest path between two locations. You want to see where is the nearest hospitals from one location. So it's good for the network analysis, vector data model. And fortunately, these two types of data models can be converted to each other. So data can be transferred from vector data model to raster data model, which we call them rasterization. And from raster to vector data model is called vectorization. And both can be done by computers, so you don't have to worry about calculation. Also note that some information is always lost when you convert from one data model to another data model. So first let's talk about the rasterization, which is the process from vector to raster conversion, okay? So this process takes two steps. First, we should impose a raster grid onto the vector data, okay? So we have a vector here, right? And first of all, you have to impose a raster or superimpose a raster grid onto this vector data, point, line, polygon, and then you have to apply the winner-take-all strategy, okay? For example, let's say we have the vector polygon data here, right? Each polygon is associated with attribute value 1, 2, 3, 4. In the first step, we have to impose a raster grid onto the vector layer, and then we apply the winner-take-all strategy. For example, for this cell, for the first cell, okay? For the first cell is completely within the polygon number of 1, right? So if we within the polygon number 1, so we have to assign the value of 1 to this cell, right, in the final result. We do have some cells that cover or intersect several polygons, okay? For example, this one, right? It's between 1 and 4. We don't know, is it 1 or 4? Then we have to apply the winner-take-all strategy. Which one is, so the most part of the cell is covered by 1 or 4 by 1. So in the output, it's going to be 1. So we should apply the winner-take-all strategy for every cell from top left to bottom right, one by one. So, and then we have vector to raster. So that is called a rasterization. But some key point about rasterization, this process is going to lose topological relationship, because no information will remain or will be kept about the relationship between the polygons, right? For example, we no longer know polygon 1 is adjacent to polygon 2, 3, or 4 in the raster format. And second, the positional accuracy will decrease, particularly at boundaries. Why? Because at boundaries we apply winner-take-all strategy. That means that the details will be missed. So every cell can only accept one value, either, for example here, either polygon 1 or polygon 4. So the positional accuracy is missed. From this figure, like this polygon, you can see positional accuracy for the vector data model is excellent, and in the raster data model is significantly decreased, okay? Or topological relationship for the raster data model is cannot be set for the raster data. Now let's look at the reverse process from raster to vector, which is called vectorization. So let's look at how to vectorize a raster line. Okay, so here the dark cell represents a raster line. So in the first step, we need to extract the midpoint. We need to extract the midpoint of every line cell, and then we will have a series of points, right, like this. And then we should link the points one by one to form a line. This is how we can convert from raster to vector for the line, right? But how about the let's say you have a raster polygon like this, okay? And each cell has a value indicating which polygon this cell belongs to. So the first step is for the polygon, for vectorization of the polygon, the first step is that you have to detect the borders of the polygon, okay? So the question is, where are the borders? And the borders will occur where the value changes, okay? For example, between these two cells, between 1 and 4, the value changes, right? So there's gonna be a border. Or between 1 and 2, the value changes, so there's gonna be a border. So we have a border here, so all of these values are 1. Between 2, all of these are 2 and 3. So the borders are where the values changes, right? So after detecting the borders, the next step is that we have to merge the values with the similar attributes, okay? So all of these values with the similar attributes gonna be 1. All of these gonna be 2, 3, 4, and again here is 1. So that is how we go from raster to vector for polygon, okay? That's vectorization of raster polygon. So now let's summarize the big picture of the data model. We have started with the real world. We talked about the human perception of the real world. The first step was to stratify the real world into layers or feature classes like buildings, roads, and so on. And each feature class can be further abstracted as points, line, polygons for vector data model, or field for raster data model. And each feature will be assigned with a spatial component, which was geographic location and shape, as well as their attributes, which were characteristics or description of the features. And then for geometry, you had two options. You can either use coordinates to describe geometry, or you can just use cells, okay? So that gives us data model. So vector data model and raster data model. Vector data model uses coordinates to describe point, line, polygon, and raster data model uses grid cells to describe point, line, and polygon. So that's the major difference between the vector and raster data model. That's the whole process of how we translate the real world in our brain into the digital format, which can also be understood by the computers. And in the following classes, we will talk about the coordinates and also attribute table.